Hello. Yes, we welcome you back to PSSB with me, Richard here. Yes, tonight we are looking at this question. It says, write the equation representing the equilibrium for autoionization of water. Okay. How do we go about that? Okay, the autoionization of water involves a water molecule reacting with another water molecule. Okay. Now, in this case, one of the water molecule acts as a base, donating a proton to the other. So, when this one receives a proton, what you get is hydronium ion. Okay? And when this one loses a proton, what remains behind is hydroxide ion. And that is the equilibrium. Yeah. Then we come to this question. It says, write the expression for water dissociation constant and write its value. Okay, I would like to tell you that the water dissociation constant, we write it the same way we write equilibrium constant. So what it is, Kw equals to concentration of the hydronium ion into concentration of hydroxide ion, which are the products, over concentration of water into concentration of water. But we have to remember that water literally remains unchanged. So what does that mean? That we leave it out. I want you to remind you that whatever we present in the equilibrium expression are changes. And if water remains unchanged, we don't put it there. It remains one. So what are we going to say? We are going to have our fine expression, which is going to say Kw giving you hydronium concentration into hydroxide concentration. And this is it. But they said we write its value. So what is the expression for Kw? It is known and presumed to be constant at 25 degrees Celsius, which is going to be equal to 1.0 or simply 1 times 10 power minus 14. Yeah. Now we come to this question. It says that referring to the value of water dissociation constant, explain the extent of ionization. Okay. We found out that Kw, or water dissociation constant, is 1 times 10 power minus 14. So when you look at this value, what comes to your mind? It is very, very small. It is 0.000000. That's around 13 zeros. So the implication we get from here is what? The implication is that water is weakly ionized, or water is poorly ionized. Yeah, that is it. The value of water dissociation constant Kw is very small, implying that water is poorly or weakly ionized. Yeah. Then comes this question. It says, calculate the pH of a solution of sodium hydroxide. of concentration 0.02 moles per cubic decimeter. How do you go about that? Okay, here you have to remember that pH is equal to negative log hydronium ion concentration. Okay. But when you look at the scenario we're analyzing, what do you see? We do not have hydronium ion concentration. We don't have hydronium ion anywhere. So what do? You set up the task of calculating hydronium ion. So you say, calculating hydronium ion concentration. Okay. That's what we are supposed to do. So what do you do here? Okay, you have your sodium hydroxide. Okay. It's in aqueous solution. So on dissociation, what do you get? You get sodium ions plus hydroxide ions. But here we have to remember something. Sodium hydroxide is a strong base. And how do you define a strong base? It's the one which is fully dissociated. So which means that we represent one arrow, or the arrow which is pointing in one direction towards the products. So which means that at the end of this dissociation, we don't have sodium hydroxide anymore. Everything is either sodium ions or hydroxide ions. This one is no more. But this is what you have to remember, that when you analyze the equation, it is balanced, and what you have here is 1. The number here in front is 1. And what you have here is 1. We have our interest is in hydroxide ions. So the mole ratio is 1:1. So which means that when this one is completely dissociated, what you have here will be exactly that. So if this was 0.02 moles per cubic decimeter, what is this one going to be at the end of the dissociation? It's going to be 0.02. Okay. So now we know the number of moles of hydroxide ions. What do we do after that? We go ahead now and quote the KW. KW helps us to change the hydroxide ions to hydronium ions. So this is the expression we have. And we know the value. What's the value of KW? It is 1 times 10 power minus 14. Okay. So with that, what do? We substitute for hydroxide because we have it now here. So it's going to be 0.02 into hydronium ions, giving you 1 times 10 power minus 14. Okay. So from here, what do we get? Now we know the concentration of hydronium ions. Okay. What are they? It's going to be this one equals to 1 times 10 power minus 14 over 0.02. This one gives you what? Yeah, so now we have the concentration of hydronium ions. The units are moles per cubic decimeter. From here, what do? You equate your equation, which is supposed to be pH equals to negative log hydronium ion concentration. Now we have hydronium ion, we can say negative log 5 times 10 power minus 13. Yeah, giving us 12.30. This happens to be the pH of this sodium hydroxide. And with that, I would like to say thank you for your time. The channel is PSSB, Physical Sciences Silver Bullet, with me, Richard, here. We urge you to subscribe, to comment, to like, to share. And we need also to remind you that Physical Sciences Silver Bullet is a YouTube science channel specializing in physical sciences grade 12, 11 and 10, and in natural sciences grade 8 and 9. We recommend that if you are using our channel, please use the playlist. Just go to playlist and click the material which belongs to your level. For grade 8 and 9, just look for natural sciences grade 8 or natural sciences grade 9. As for grade 11 and 10, look for physical sciences grade 11 or physical sciences grade 10. For grade 12, every topic is presented independently. So just look for the topic of your interest and click on it. There you are. You'll have all the information which you need. With that, I would like to say thank you. We appreciate you. See you next time. Bye-bye.